Okay, so we're going to start looking at acid-base equilibria 2. Now remember, we've kind of already done this introductory thing here before, but just to recap, you know, HCl, what's stronger, HCl or vinegar? Well, HCl is a strong acid. It's a mineral acid because it has an inorganic anion. Okay, strong acid, if you like a mineral acid. Okay, why is it strong? Because remember, 100% dissociates. So, you know, 100 molecules give you 100 H plus ions if it's monoprotic. Okay, if I have vinegar, and I like to write the anion in brackets, you won't see that in the book, but I do that because it kind of emphasizes that's the acidic proton. That's a weak acid, and it's partial dissociation. Okay, now if you remember, we did this before. We'll just go over it again just to show you. Okay, so a strong mineral acid dissociates completely. How do you represent that? Oh. The single arrow. Okay, the single arrow means completely dissociated. ICE. Initially 100 moles, 100 molecules, 100%, 0 and 0. Every molecule breaks apart. I make 100 H plus and 100 Cl minus. 2 passengers per car. The car stops. 2 people get out. 100 cars stop. 100 guys and 100 girls get out, if that makes sense. Okay, what's left at equilibrium? Just the difference, 0, 100, 100. 100% dissociated. Okay, for weak acids, a little different. I'll do a generic, HA. Weak acids are in equilibrium, so there's always some undissociated acid and dissociation products at equilibrium. Generic, A minus. Okay, so ICE, same thing. Initially 100, 0, 0. Let's say for fun it's different this time. Let's say it's 5% dissociated. Minus 5, plus 5, plus 5. 95% of the molecules remain intact. 5 H pluses, 5% A minus. So, oh, keep forgetting to shove it up there. There we go. All right. So, moving on. So obviously, because weak acids are in equilibrium with their dissociation products, we can treat them with equilibrium math. Okay, so look at a generic example. So here we have a weak acid, and we say we react with water to make the hydronium ion, but we'll show you the simpler version again in a second, and the conjugate base. Okay, so if I write, you know, just straight equilibrium constant, products over reactants, I get that. Okay, now obviously water is a constant, so a constant times a constant is a constant. So K times the concentration of water, which is a constant, equals a new constant. We call it the acid dissociation constant, which is H3 plus O, A minus over HA. So products over reactants. Now remember, H plus, H3O plus are synonymous, and what you'll see in the book is that version right there. Okay, so every weak acid has a Ka, an acid dissociation constant, which is an equilibrium constant, products over reactants. Interestingly, one of the products, of course, is H+, and we can get into the concentration of that through pH, which we'll show you in a little bit. Okay, so discussion then. Will strong acids have a large or weak Ka? Well, if we think about it, they're 100% dissociated. So products is 100, reactants is 0, so it's effectively infinity. Right? It's no such thing really, of course. It's probably 10 to the 6 or bigger for Ka. Okay, so for HCl, Ka is approximately infinity. Okay, because it's 100% dissociated. It's really, 10 to the 6 or bigger, but we kind of say tends to infinity. Okay, so for weak acids, that's strong. Weak, Ka is in a measurable range, and it's small. It's a little bit of product. It's between 10 to the minus 3 and 10 to the minus 10. So the ratio of products to reactants is between 1,000th and 1/10 billionth. Okay, so 10 to the minus 3, 10 to the minus 10. Oh, do that up. Keep forgetting to do that. There we go. So with that in mind, we can look at some very simple kind of acid dissociation schemes. So if we look here, these are both mineral acids. They have, common, we've seen these before, mineral anions. Okay, so they're both strong. So, HCl and nitric acid are strong. So nitric acid would 100% dissociate. And it's approximately infinite in terms of its Ka. Okay. Now down here, we have weak acids. How do you know these are weak? You may think, oh, HF, HCl, HF, maybe it's strong. Well, actually it isn't, for reasons we can get into another time. But if you look over here, they all have measurable Kas. If you have a measurable Ka in the range 10 to the minus 3, 10 to the minus 10, something around there, something measurable, it must be in equilibrium. Okay, so they're all weak. And they're all in equilibrium. That's how you'd say it written in the book. I'm going to do my normal thing. That's vinegar, acetic acid, completeness. And finally HCN. All right, so there we have it. 3 weak acids, all showing equilibria with measurable equilibrium constants. Now, interesting question down here. Of these 3 weak acids, which is the strongest of the weak, the king of the nerds, right? Strongest of the weak, and which is the weakest? It's easy to figure out. If you think about it, Ka is a measure of products over reactants. Products are H+, so the bigger the number, the more H+. Which of these has the bigger dissociation constant? Well, it's the first one. Okay, so that's the strongest of the weak, and this is the weakest of the weak. Okay, there we go. So the strongest is HF, strongest of the weak, Ka largest, and HCN weakest of the weak, Ka smallest. Okay, I like to do this because it kind of shows some kind of understanding. Equilibrium lies to the left. This guy at the top here, equilibrium lies to the right. Okay, moving on. So as I mentioned, H+ is a product for every weak acid. So what we can do is wait for my computer to catch up here. Oh, there we go. You probably didn't see that at your end, but having some technical difficulties here, my end with a bit of lag. But we can incorporate pH into a calculation for Ka, or use Ka to work out pH. So we go backwards or forwards. Okay, and we're going to use the ICE method. Yes, corny joke. Vanilla ice, obviously a noted chemical philosopher. Okay, now If we want to find the pH, how do we do that? Well, remember, nice and easy. Okay, actually, let's read the question obviously first. So, word example, a sample of 0.1 formic acid, that's the formula. That's what ants actually inject you with if you're interested. So ant venom stings because it has an acid in it. Okay, so 0.1 formic acid has a pH of 2.38. That's an important number. Find Ka. So this is the finding Ka from pH example. Okay, so, and then once we've done that, we can find out the percent of dissociation, which is an interesting number. All right, so plan, do a couple of things. Find the H plus concentration from pH, and then hey, once we've got the H plus concentration, that's a product, remember, in our ICE table, so we can then go run it backwards if you wish to find Ka. So find H plus first. Now remember, pH minus log of the H plus ion. So if I do a little bit of math there, I'll leave H plus over here just to show you, right? So I move the sign over there, minus pH equals log of H plus, and then 10 to that, that'll cancel, equals H plus. So H plus concentration equals 10 to the minus pH. In our example, 10 to the minus 2.38, which equals 4.2 times 10 to the minus 3 molar. All right, so the concentration of H plus, 4.2 times 10 to the minus 3 molar. Now, that's it. If you remember our classic way of doing an ICE table, and I'll set it up in the classic way. Okay, so acid in equilibrium with its dissociation products. I, C, E. Okay. 0.10, 0, 0. We don't know how much it loses, but it's x plus x plus x. It's in a 1 to 1 to 1 ratio. Okay. All right. Before in our previous kind of example a couple of pages ago, that was like 5, right? But we've got to find out what it is. Okay. So 0.10 minus x, I'll keep that together. X and x. I like to kind of emphasize that. That's at equilibrium. Okay, so at equilibrium, K applies, right? So K is products over reactants as our kind of algebra way of doing that. Now, if you think about it, what have we got here? We've got equilibrium values, right? So at equilibrium, concentration of H, CHO2 equals 0.10 minus X. Concentration of H plus equals X. Aha! It's our number from before. 4.12 times 10 to the minus 3 molar. And because it's equimolar, 1 to 1, CHO2 X, which is the same number. Okay, so I'll do the algebra work up on the next page, but those are the numbers that we're going to throw in. Okay, so Ka equals products over reactants. That's in that formula. H, C, HO2. All right. Which equals, go back to the previous page. Both of these were x. X times x is, of course, x squared. Divided by reactants at equilibrium 0.10 minus x. Now, here's an interesting thing. This is called the weak acid approximation. Since x is super small, 4.2 times 10 to the minus 3, so 0.004 to two significant figures, 0.10 minus 0.004 is 0.1, okay? So that's always small. So a big number minus a small number is the same big old number. We call that the weak acid approximation. And it's essentially equal to x squared over 0.1. And we can always make that weak acid approximation. We'll meet it formally in a minute. But if you've got a weak acid, Ka is always small, 10 to the minus 3 or smaller. So therefore, a big number minus a small number, same number. Oh, substitute for x on top if we're going to do that. 4.2 times 10 to the minus 3 squared. Finally, at the end of the day, 1.8 times 10 to the minus 4. 1.8 times 10 to the minus 4. Okay, how'd that make sense? Remember, always, we've seen a common theme. You basically do yourself a grid, an ICE table. And it doesn't really matter what kind of equilibrium it is, okay? You can always figure it out from that table. Remembering that the bottom line, I'll show you back again. The bottom line down here is the equilibrium position as defined by K up here. All right, so the percent dissociation, think about it. If I want to figure out how much dissociated, it's what I got over what I started with times 100. So percent dissociation, the H plus at equilibrium over what I started with, HA initial times 100 for a percent, which equals 4.2 times 10 to the minus 3 over 0.1 times 100, 4.2%. So about as strong as vinegar. So ants are essentially injecting you with vinegar. I guess that hurts, right? There we go. So that's the first one. That's, if you like, the forward direction, work out Ka from the pH. You can, of course, run it backwards and work out pH from Ka. So the plan there would be, okay, and here's a problem down here. Again, I'm having a bit of lag here. Bear with me while I just position the paper. There we go. All right, so the plan is, again, do an ICE grid, okay? Work backwards to find H plus from Ka. So we'll rearrange that algebra. Okay, and then once you got H plus, you can solve for pH. All right. So let's go. So the grid, it was 0.2 molar HCN and its Ka was given, okay? So we got HCN in equilibrium with H plus and Cn minus aqueous, of course. All right. ICE 0.200, do the usual procedure. It's monoprotic, right? So it's 1 plus 1 plus 1, don't know how much, that's X. 0.2 minus X. And again, that's weak acid approximation, 0.2, X and X. All right. Ka then equals products. This one times this one, which is X squared, over 0.2 minus X, which again is approximately equal to X squared over 0.2. That's the weak acid approximation again. Okay, because we assume that X is super small compared to 0.2. All right, therefore flip back, Ka was 4.9 times 10 to the minus 10, X squared over 0.2, therefore X equals H plus, which is what we're after, that's our focus, which equals this times this square rooted 9.9 times 10 to the minus 6. Therefore, pH equals minus log of H plus minus log of 9.9 times 10 to the minus 6, which equals 5.0. Okay, oh, again, off the bottom of the page, excuse that. Okay, so I just ran the algebra. Ka x squared, just rearranged to find x, which is H plus, minus log of H plus. Okay, and there's a formalization of the weak acid approximation. Okay, now it says group work. Okay, we got a couple of old exam questions on this. Okay, and what I'm going to do, which is kind of neat, I'm actually going to assign this for a little bit of extra credit homework. Okay, so what I'm going to do, this is the interesting thing. Okay, work out problems take a picture of all your work on your page and then send as email attachment. I'll make it worth 5 points. Actually, make it worth 6, 3 each, because there's 3 times 2 points. There's 2 questions, right? Okay. So if we go to the back of the book, the back of the packet, right, we'll do weak bases in the next thrilling installment, right? Okay. So that's the next packet. Sorry, that's the next video. Okay. In the back of the packet here, we have a couple of old exam questions, all right, and both of these are going to be worth 3 points of extra credit. Okay, what's the pH? So I've got, it's my classic favorite question, the same concentration each time, but I've got 3 different acids. I've got a monoprotic, diprotic, both are strong, then a base, okay, and then a weak acid, and you do the whole grid thing. Okay, so you get 3 different pHs for 3 different solutions, all of the same concentration. I like that question a lot. So work on that. Send it me. I'll put in the, you've probably read it, in the discussion, I'll write a deadline for that. Probably give you a week, all right? And then the next one, weak acid, it's a more formal weak acid. We're actually going to work out a bunch of things. Got a weak acid, and you're working backwards, so check the previous question when we work out the percent of dissociation. Work backwards to find H plus, HA, and Ka for this. That's at equilibrium. Okay, the equilibrium concentrations of H plus and HA and Ka for that solution. All right. All right. Of course, you can use the weak acid approximation. So big hint. Yeah, it's the same number, isn't it? Okay. All right. So we'll do the weak base one after we finish the weak base work. All right. So I'll stop there. Any questions? Please feel free to comment in the discussion area, and we'll see you on the next one.